Here's an example of what I mean of how I might go about doing the a calculation of the resonant frequencies of a system. So here what I have is the kinetic energy and potential energy of a system where I have let's see, a spring hanging down from the ceiling and then a mass at the bottom of that, and then another spring hanging below that, and a mass at the very bottom of that. Okay, so let's see here. So the kinetic energy of one is just given by its velocity squared, times 1/2 mv squared, and then kinetic energy of the other is 1/2 mv squared of the other guy. So in Mathematica, the primes represent derivatives. Um, the potential energy is mgh, essentially, at negative because it's going down, but you also have a couple of springs, and I'm defining happy 1 to be the happy length of the first spring. So you have 1/2 kx squared, essentially. And then the other one, you have to get the difference between the two mass locations minus the happy distance of the second spring squared. The Lagrangian is just the kinetic energy minus the potential energy. I've got this power function. You use the power function to put viscous friction in there. I'll show you that in a second. And then my Lagrangian is the derivative of the Lagrangian with respect to the variable minus the derivative of the Lagrangian with respect to the variable primed, and then a time derivative of that. And then this is how you get viscous friction in the Lagrangian, set that equal to 0. Next I've got some constants. I just make it very boring. Both masses are 1. The spring constants are both 100. The happy lengths are 1. And what I do is I do a ndsolve command. So I do the Lagrangian for both x1 and x2. I set them both at their happy distance. Well, x2 really needs to be happy 1 plus happy 2 because it's actually measured from the very, very top. I decide to set them both not moving at all, so that's what this initial condition here is. And then I just ask Mathematica to solve for x1 and x2. Note that I have a decent amount of friction in here, so I'm expecting this after 10 seconds to settle down. So when I evaluate that, sure enough, the first one settles in here at about 1.2 or so, and the second one, so it started at 1, but it settles in at 1.2. The second one started at 2 and settles in at about, 2.3 or so. And so what we're wondering about is if we let this thing move around from these locations. So let's just deviate them from these locations a tiny little bit and see what happens. So when I do those, I need to ask where are those equilibrium locations. So I ask Mathematica to please tell me those, and it gives me that. Then I come back and I resolve, and this time I'm setting the friction to 0. And I resolve where I set them to their equilibrium locations, but I adjust them by some very small 0.1 distance, a random number, could be positive or negative, and again I have them set at rest and I evaluate. So when I plot their motions, they're both doing some crazy things, but when I Fourier transform one of them, so this would be just a set of data to be Fourier transformed, and this is now a log plot of the frequencies. You can see that there are two clear resonant frequencies, and so this would be the type of analysis that I would have my students do. The last part would be to sort of isolate each of these and to look for exactly how each one moves, or possibly to excite the system by maybe moving the ceiling up and down at either this frequency or this frequency.